All right, I know you're probably itching to dive into some code by now, but there's a little more theory we need to cover with deep learning. I want to talk a little bit about exactly how they are trained and some tips for tuning them now that you've had a little bit of hands-on experience with them using the TensorFlow playground. So how do you train a multi-layer perceptron? Well, it's using a technique called backpropagation. It's not that complicated really at a conceptual level. All we're doing is gradient descent like we talked about before, using that mathematical trick of reverse mode autodiff to make it happen efficiently. For each training step, we just compute the output error for the weights that we have currently in place for each connection between each artificial neuron. And then this is where the backpropagation happens. Since there's multiple layers to deal with, we have to take that error that is computed at the end of our neural network and backpropagate it down in the other direction, push it back through the neural network backwards. Okay, and that way we can distribute that error back through each connection all the way back to the inputs using the weights that we are currently using at this training step. Okay, so pretty simple concept. We just take the error, we use the weights that we are currently using in our neural network to backpropagate that error to individual connections. And then we can use that information to tweak the weights through gradient descent to actually try and arrive at a better value on the next pass, at the next epoch, if you will, of our training passes. So that's all backpropagation is. We run a set of weights, we measure the error, we backpropagate that error using that weights, tune things using gradient descent, try it again, and we just keep doing this over and over again until our system converges. We should talk a little bit about activation functions. So in our previous exercise using the TensorFlow playground, we were using the hyperbolic tangent activation function by default, and then we switched to something called ReLU, and we saw that the results were a little bit better. What was going on there? Well, the activation function is just the function that determines the output of a neuron given the sum of its inputs. So you take the sum of all the weights of the inputs coming into a neuron. The activation function is what takes that sum and turns it into an output signal. Now, like we talked about way back in Lecture 1, using a step function is what people did originally, but that doesn't really work with gradient descent because there is no gradient there. If it's a step function, there is no slope. It's either on or off. It's either straight across or up and down. There's no useful derivative there at all. So that's why alternative functions work a little bit better in practice. There are some other ones called the logistic function, the hyperbolic tangent function. That produces more of a curvy curve. If you think about what a hyperbolic tangent looks like, it's more of a it doesn't have that sharp cutoff there at 0 at the origin, so that can work out pretty well. There's also something called the exponential linear unit, which is also a little bit more curvy. What we ended up using, though, was ReLU. That stands for rectified linear unit, and that's what this graph here is showing. Basically, it's 0 if it's less than 0, and if it's greater than 0, it climbs up at a 45-degree angle. So it's just, giving you the actual sum of the input weights as its output if that output is greater than 0. Okay, so the advantage that ReLU has is that it's very simple, very easy and very fast to compute. So if you're worried about converging quickly and you're computing resources, ReLU is a really good choice. Now there are variants of ReLU that work even better if you don't care so much about efficiency. One is called leaky ReLU, and all that is instead of being flat left of 0, it actually has a little bit of a slope there as well, a very small slope. And again, that's for mathematical purposes to have an actual meaningful derivative there to work with. So that can provide even better convergence. It's also something called noisy ReLU, which can also help with convergence. But these days, ELU, the exponential linear unit, will often produce faster learning. That's kind of it's gaining popularity now that computing resources are becoming less and less of a concern, now that you can actually do deep learning over a cluster of PCs on a network in the cloud. So that's what activation functions are all about. You can also choose different optimization functions. We've talked in very general terms about gradient descent, but there are various variations of gradient descent that you can use as well. We talked a little bit earlier about momentum optimization. Basically, the idea there is to speed things up as you're going down a hill and slow things down as you start to approach that minima. So it's a way of just making the gradient descent happen faster by kind of skipping over those steeper parts of your learning curve. Wow, I never used the word learning curve in the context where it actually means something mathematically meaningful. But anyway, there's also something called the Nesterov accelerated gradient, which is just a tweak on top of momentum optimization. Basically, it's looking ahead a little bit to the gradient in front of you to take that information into account, so that works even better. There's also something called RMS prop, which is just using an adaptive learning rate. That, again, helps point you in the right direction toward the minimum. If you remember back to how gradient descent works, it's not always obvious which direction you're going to be heading in given a change in parameters. So RMS prop is just a more sophisticated way of trying to figure out the right direction. Finally, there's something called ADAM. It stands for Adaptive Moment Estimation. Basically, it's the momentum optimizer and RMS prop combined. Kind of gives you the best of both worlds. And that is a popular choice today because it works really well and it's very easy to use. Again, the libraries you're going to use for this stuff are very high level and very easy to use. So it's not like you're going to have to implement Nesterov accelerated gradient from scratch. You're just going to say optimizer equals ADAM and be done with it. It's just a matter of choosing the one that makes sense for what you're trying to do. Make your own trade-offs between speed of convergence and computational resources and time required to actually do that convergence. Let's talk about overfitting as well. You can see you'll often end up with patterns like this where, you're not really getting a clean solution. You end up with like these weird spikes sometimes. And sometimes if you let things go a little bit too long, it ends up reinforcing those spikes, those overfitted areas where you're not really fitting to the pattern you're looking for. You're just fitting to the training data that you were given. Okay, so there are ways to combat that. And obviously, if you have thousands of weights to tune, those connections between each neuron and each layer of your neurons can add up really quickly. So it is very easy for overfitting to happen. There are ways to deal with it. One is called early stopping. So as soon as you see performance start to drop, that might be nature's way of telling you that it might be time for you to stop learning. At this point, maybe you're just overfitting. There are also regularization terms you can add to the cost function during training. That can basically like the bias term that we talked about earlier, that can help too. But a surprisingly effective technique is called dropout. And again, it's an example of a very simple idea that is very effective. The idea is just to ignore, say, half of the neurons randomly at each training step. Pretend that they don't exist at all. And the reason this works is because it forces your model to spread out its learning. If basically you're taking away half of its brain, if you will, at each training step, you're going to force the remaining half of those neurons to do as much work as possible. So this prevents things where you have individual neurons taking on more of the work than they should. You even saw in some of the examples that we ran in the TensorFlow playground that sometimes we'd end up with neurons that were barely used at all. And by using dropout, that would have forced that neuron to have been used more effectively. So very simple concept, but very effective in making sure that you're making full use of your neural network. Let's talk about tuning your topology. Another way to improve the results of your deep learning network is to just play games with how many neurons you have and how many layers of neurons you have. One way of dealing with it is just trial and error. It's kind of what we did in TensorFlow Playground. But, there can be a methodology to that even. You can start off with the strategy of evaluating a smaller network with less neurons in the hidden layers, or you can evaluate a larger network with more layers. So basically you want to see, can I get away with a smaller network and still get good results? And just keep on making it smaller and smaller until you find the smallest it can be safely. Or you can try to make your network larger and larger and see, at what point it stops providing more benefits to you. So, just start sizing things differently and see what works and what doesn't. Again, there's sort of a spooky aspect to how this stuff all works together. It's very hard to understand intuitively what's going on inside of a neural network, a deep learning network in particular. So sometimes you just have to use your intuition to try to tune the thing and get at the right number of resources you need. Also, again, in today's modern computing environments, sometimes you don't really care so much. It's probably okay to have a deep neural network that has more neurons than it really needs, right? I mean, what's the real expense involved in that these days? Probably not much. I will say that more layers will often yield faster learning than having more neurons and less layers. So if you care about speed of convergence, adding more layers is often the right thing to do. Or you can also use something called model zoos. There are actually libraries out there of neural network topologies for specific problems. So if you don't think you're the first person in the world to solve a specific classification problem or anything else you're trying to apply a deep neural network to, maybe you should check out one of the model zoos out there to see if someone's already figured out the optimal topology for what you're trying to achieve instead of trying to reinvent the wheel. Okay, people share these things for a reason, and it can save you a lot of time. So that's enough theory, that's enough talk. In our next lecture, we'll get our hands dirty with TensorFlow and start writing some real Python code to implement our own neural networks.